Before I begin, I just want to quickly thank Michael from Australia who introduced this flat earth proof to me. Now, the fact that no airplane has to dip its nose to account for the curvature of the earth is a common proof of the flat earth. Essentially, if we lived on a globe, an airplane that is maintaining straight and level flight in a short amount of time would have to dip its nose to account for the curvature of the earth. As an extreme example, an SR-71 going Mach 3.2 or 2,455 miles per hour at 80,000 feet, where the air pressure is very little, would need to drop approximately 1,117 feet every minute to maintain level flight. But even a small Cessna 172 at 9,000 feet, traveling 140 miles per hour, would still have a curvature adjustment of over 3,200 feet in just 30 minutes. Regardless of altitude or speed, those curvature adjustments never happen. But that is not the point of this video, and this flat earth proof may even be better. Whenever an airplane is approaching its destination, the pilot must work out at what point in the flight where the airplane should begin descending. This is referred to as top of descent, or the point at which descent is first initiated from cruising altitude. From top of descent, the general rule is that all aircraft will descend at an angle of 3 degrees. The glide path, or glide slope, means the proper path of descent for an aircraft preparing to land. The reason why the term glide is used is because it's ideal for the airplane engines to be idle while descending to optimize fuel consumption. An ideal idle descent uses the minimum fuel, minimizes pollution, both at high altitude and local to the airport, and minimizes local noise. Here's a pilot describing it.
Ideally, we want to fly from 38,000 feet at top of descent and assume a 3-degree glide path all the way down until we're ready to configure the aircraft for a straight-in approach. We want to, during the descent, keep the engines in idle. If we can, from top of descent until we start configuring the aircraft, keep the engines in idle, then we have obtained the lowest possible operational cost.
Nowadays, top of descent is calculated by the flight management system and autopilot, but it all uses the same trigonometry, and a good pilot still continually applies rule of thumb calculations to make certain that the computer is correct. As a rule of thumb, top of descent is simply calculated by the change of altitude, current altitude minus the traffic pattern altitude at the destination, divided by 1,000 and multiplied by 3. That will give you the flatline ground distance from the airport to the top of descent point in nautical miles. That is a good rule of thumb, but to be exact, you use trigonometry. Once we know the angle and the altitude of the airplane, a pilot can use trigonometry to calculate the distance to where to begin top of descent. Whenever you hear the word trigonometry or right angle, your alarm bells should be going off, because you can't use trigonometry and a right angle with a curved baseline. That's the same reason why the sextant in celestial navigation proves a flat earth. So let's assume a top of descent altitude at 38,000 feet and a traffic pattern altitude at 1,000 feet. Let's start with our simple rule of thumb calculation. We take 38,000 feet minus the 1,000 feet traffic pattern altitude, and that's assuming an airport elevation at sea level. We divide that by 1,000, which is 37, and multiply that by 3, and that gives us 111 nautical miles, which converts to 128 miles. Now let's make the same calculation using a trigonometry calculator. We still figure out the change of altitude by subtracting 38,000 feet minus the traffic pattern at 1,000 feet, which is 37,000 feet. We input 37,000 feet altitude for side A, and then put in a 3-degree glide path angle for uppercase A. That gives us a ground or side B distance of 706,002 feet. Divide that by 5,280, and we get 133.7 miles. That means the top of descent should start at 133.7 miles away from the runway. A pilot will generally want to stay on that straight glide path all the way to the target. Here's the major globe problem. At 133.7 miles, what is the curvature drop if we lived on a ball? Plug in our amounts, and we get a curvature drop of 11,917 feet at that distance. You reach the same results with the 8 inches per mile squared calculation. Do you think 11,900 feet would be important for a pilot? Of course it would. Here's another example from simpleflying.com with a top of descent altitude of 35,000 feet. It's the same trigonometry, but let's use our online calculator. We get the amount of 667,840 feet, which equals 126 miles. What's the curvature drop at 126 miles? 10,665 feet. Do you think 10,665 feet would be important for a pilot to consider? Of course it would. This is similar to the problem discussed by the retired F-16 pilot, where the radar sweeps and targeting system of the F-16 are based on a flat Earth and never consider the substantial curvature changes. If we lived on a globe, the Earth's curvature would result in enemy aircraft appearing much lower on radar, resulting in errors when the F-16 is intercepting other aircraft. But in determining top of descent and descent management, and as we already discussed, a pilot does consider the elevation of the airport, the traffic pattern altitude, which is typically around 1,000 feet. The pilot makes adjustments for wind direction, and weight of the aircraft. But a pilot never makes an adjustment for the curvature drop. Do you see what would happen if we lived on a globe and the pilot did not consider curvature drop? In our example, the runway would be 11,917 feet lower than the pilot originally calculated. In short, the top of descent calculation is computed with trigonometry, which requires a flat distance baseline contradicting the globe. More importantly, because the substantial amount of curvature drop is never considered or added to the plane's altitude to make the top of descent calculation, the globe is proven false. Thank you for watching.